Hi, so I'm Catherine Scott. I work over at Intrinsic. Generally, I'm the ROS developer advocate. That's why a lot of you know me. The best part of my job is I get to see the baby startups grow up. So I remember when Adrian, this was all a twinkle in Adrian's eye. So this is very exciting to see. We've got only 30 minutes here, maybe 35 if we're lucky. So I'm going to kick it off by having everyone basically introduce themselves, talk about their role in their organization, and then talk a little bit, if you use simulation, how you use simulation, if you don't use simulation, why you don't use simulation. But keep it to 2 sentences. Keep it really pithy. This is the lightning round. So why don't we just go left to right?
Is that me?
Stage.
Is it on? Okay, good. Hi, I'm Allison Thackston. I have a pretty long history in robotics. I started working with space robots with NASA on the Robonaut project. I moved into home robots with TRI, moved into the autonomous vehicle space with Neuro and Waymo, and now I do autonomous tractors at Blue River. And through the entirety of my career, I've always used sim. Part of the stack that I mostly work in is the planning stack. And I've definitely found that sim is super useful for being able to understand how good your algorithms really are, plus using it in the real world. At Blue River, we are trying to build up more of our simulation capabilities. I think we use a lot of live tractors at the moment to do the majority of our testing, but I'm really trying to build up the simulation stack since I have found it so useful in my past experience.
Hi everyone, I'm Simon. I'm CEO of Resim. Oh, yeah. And I have one fan in the audience. I'll write the check later. That's great. CEO of Resim AI. We build plug-and-play virtual testing infrastructure for robotics and AI engineers. Our platform works with actually any kind of virtual testing software, including all simulations. What we do is we help you scale up. So we unlock cloud infrastructure execution at scale and rich insights and metrics with features like A/B testing, longitudinal statistics, coverage analysis, and much, much more. Like Allison, I and actually a lot of the Resim team are alumni of the self-driving industry, where we saw people build huge in-house simulation efforts and run millions of sims a day. Getting to that kind of scale can be hard, and so part of the idea of founding Resim was helping companies get out the starting blocks and, with only a handful of engineers who are building some cool sim tech, get them on the path to Waymo scale without having to hire a Waymo-sized team.
Hi, everybody. My name is Kathleen Brandes, and I'm the CTO of Adagy Robotics. And before starting Adagy, I worked at Tesla on autopilot motion planning, where I also got to use sim a lot to do initial testing. And I also worked at Boston Dynamics, where we built the in-house sim and fought those battles pretty significantly. Today with Adagy, we are a human-in-the-loop teleoperation service, and we use simulation to test different APIs to mock out different robot scenarios and make sure our operators are fully trained before they actually start using a real robot.
Hey everyone, I'm Ilia Baranov, CTO of Polymath Robotics. We're a about almost 3-year-old startup doing industrial autonomy, so think tractors, mining, forestry, ports and airports. We kind of do a wide-ranging software layer, so try to keep as much away from the hardware as we can, even though it makes my heart hurt a little bit. And I want to give a quick shout out. We run a really fun podcast called Automate It. If you want to hear the unfiltered take, go there. We use simulation, especially in early days, because a lot of our fleet is so heterogeneous that we need to be able to quickly iterate and understand what is the customer trying to do, what sensor makes sense in what position, under what circumstances. And so we have that pipeline reasonably well built out, and get more and more skeptical as you get closer and closer to prove everything out in sim and production. So I'm on that end of the spectrum. And I think we get even more skeptical as we go to my right. So heading it over.
All right. So I'm Rajat Bhageria. I'm the founder and CEO of Chef Robotics. We make AI-enabled robots for the food industry, as you can imagine. We're starting with more kind of industrial kitchens, right? So and a big volume, but a lot of mix. And then over time, the idea is that serves as data ingestion engines that allow us to then learn how to manipulate food, which we can ultimately kind of take to commercial kitchens, all commercial kitchens, right? So the thing with food, of course, as you can imagine, is it's very highly dimensional. If you cut it differently, cook it differently, it behaves very differently. And there's not really good physics simulators for food, is what we found. So I think our approach has very much been like focus on production, shipping robots, and using production data. And that's, I think, very robust. It's very scalable. It actually kind of scales to different customers, right, without having to make a bunch of custom software or hardware. Where we are using a lot of sim is kind of everything else, right? So like, going from pick to place, not hitting the tray, not hitting the conveyor, not hitting collision avoidance, all these things. So
Wonderful. So we talked earlier today about sort of knobs you can turn in robotics, and one knob I always think about is on one side you can do everything in simulation, and then you don't really test in the real world, or then you just test in the real world and you don't have simulation. And testing in the real world has a lot of downsides, right? It's dull, dirty, dangerous. Personally, I've injured myself testing robots. I've been stuck out in the middle of Boston in the winter at 3 a.m. testing robots. It's dull, dirty, dangerous. So I'd like to hear your guys' feelings on where in turning that knob from left to right between simulation and actual real-world testing. Where do you fall? Where do you feel the real value proposition is? And what's working well, what's not working well in that sort of space. So why don't we go the other way around? So why don't we go from my right to my left?
Our thinking is like, let's catch as much as we can. Let's validate as much as we can in sim before we get to the field, right? Because we don't want to get to the field and there's some small thing we could have caught earlier, right? We can also do things like figuring out where to put robot arms and cameras and basically pose optimization there. But I think that the thing that's hard about Chef, right? The thing that keeps us up at night and the hard is actually manipulating these ingredients that are slimy and wet and deformable. It's like, how do you pick a blueberry without crushing it, or how do you pick a cranberry that's sticky and it's gonna it has different physics that are hard to understand. So I think it's like, yes, let's do that going to start, but then let's very quickly get to the physical world to really learn. Now I guess what we are trying to do is figure out, okay, can we use simple particle simulation to kind of do some basic stuff, right? It's not going to be the same, and it's kind of like AV. If you think about AV, everyone kind of has these giant sim teams, right? And they spend a lot on it, but then they do have to have hundreds of thousands of miles on the road to actually validate. And I think the vision would be we can get there with food. Even if the physics simulators aren't good, we can we can develop in sim with particle simulators, and then we really validate in production and use that to refine the models.
Yeah. On our end, because we deal with a lot of very large machinery, safety is a big part. And if anybody's ever had to come near Simulink, the pain that comes with working with Simulink. It's the best tool, and I wish it didn't exist, is basically the summary. So that is a big gap right now, at least personally, or for my company in this field of safety certification in simulation and getting to reality and proving out behavior, proving out performance. And that's a problem. We're working on it. But here's a really fun challenge. We're trying to automate, let's call it a front-end loader. It's a big machine. It's about 10 tons, has a big scoop at the front to pick up material. The legitimately hardest part of simulating that entire thing, not the hundreds of components, not the physics, it's the pile of sand that it has to pick up and actually scooping in such a way that's even close to reality. Because if you try to scoop sand, you'll notice it doesn't just deform into a perfect triangle again. Huge gap. And my house for somebody who can figure that out.
Yeah, I think I would have to agree with a lot of what's been stated so far. Where I found sim most useful is actually software validation, and so it works really well for Adagy because we work on top of robotics companies' APIs, which means we let them solve the problems of scooping the sand or dealing with the blueberry, and can issue kind of calls that operate just a little bit higher than needing perfect sim and perfect physics inside of your simulation. And so it gives us a really nice pipeline to test full network setups, make sure that our operators understand how buttons work inside of our system, and fully kind of work out any kinks in the process of resolving an edge case or an error for a robot. So for us, simulation's been a really powerful tool and a really nice thing to use. I think in the past at Autopilot, we found it basically also still helpful for software validation, but as mentioned, insufficient for fully understanding exactly how the car will behave in the real world.
So, Kat, I definitely don't want you to get injured again, but I think you're still going to need to do real-world testing with robots. So where I've seen this work really, really well is where real-world testing is the first step in the sort of data pipeline that feeds in to a great virtual testing stack. So, the real world serves up really interesting experiences beyond what humans can think about. Humans are very bad at designing scenarios, just thinking about them. And so you go to the real world, you encounter your robot encounters an interesting novel event, and that's gold dust. So you don't want to let that slip through your fingers. The first thing you want to do is capture it so that you can replay it, and you can replay it through new versions of your AI. Some people call that simulation, like resimulation. Some people would argue that isn't simulation. I think it's valuable. But the next thing you want to do is actually capture it and turn it into something like a simulation so you can edit it, because then you can have more variations of this interesting event. And now you've got multiple versions of it you can test as well as train with that interesting event. And then beyond that, I think if you have very large data sets of real-world experimental data with robots, you can train models. So models for behavior, we've done some really cool stuff with behavioral models for drones that we've just learned from data. Waymo had a great paper at CVPR this year using diffusion models to model pedestrian trajectories, all learned from their amazing log data set. And also world modeling is a super exciting theme, and you need those real world robot data to train the world model to then have the simulation. So I think we mentioned that it can be useful that there's a last step validation, real world validation, but I also think it's really useful at that first step, feeding the data flywheel.
Cool. I guess for me, I think if you're making a robotic product, like, it has to work in the real world full stop, right? And so I think that's often where companies will start. They're experimenting with a real world robot. They're creating an MVP, and maybe they're just iterating on the one piece of hardware or whatever that they have. Where I found Sim really useful is when you actually try to scale it. And I think this is one of the biggest deltas I've noticed between, like, applied research, which I was doing in the beginning of my career, to more of the product-focused things that I do now, is that in order to actually get that scale, you have to be able to cover a lot of the long tail. So like Simon was saying, you have a really interesting scenario, you don't want to lose that. You want to be able to understand how your software will react to those types of scenarios. And it also it frees you up to develop decoupled from your hardware. So like for Blue River, for like autonomous tillage, right? Like there's a season, right? Like you have to do the field. There's a narrow window of time when that needs to happen, or else like you've missed the season. The farmers need to plant things. And so like if you can take advantage of that data off of that, like, couple months where it's really important for your product to work, then you can actually like iterate off season. You can do a lot more. So I think that's how I've definitely seen simulation going from like, you don't really do a lot of it in the beginning, and then you use it to bootstrap yourself into more and more scale so that you can make that like Waymo quality of like of hitting the far end of the tail.
Okay, I want to ask a question real quick. Just quick show of hands, we don't need to dive into it, but who here has basically a pipeline from real world test case back to simulation? Like, is this something that's occurring regularly?
Is the pipeline me typing on the computer?
Yeah, I'll allow a little bit of scripting, yeah, because... Oh, you? I mean, we probably all want it to be one click, right? Where it's just like, this weird thing happened, can we feed it back?
Not even click. The robots should just figure out that something's wrong and train themselves. That's the dream, right?
That's the dream. I think we're ways away.
Is typing. Lots of typing.
Lots of interns, thousands of interns. So we talked a little bit about the reinforcement learning side of this here, simulation too. Do you guys feel like simulation is supporting this well? Do you feel like the simulators are supporting this? Do you feel like this is something that's going to continue to grow? I'd love to hear everyone's sort of opinion on this sort of closed loop between simulator and reinforcement learning, and what do you think that's going to look like in a couple years?
Yeah, I mean, I think we're doing some research on this. It's like very, very early stage stuff, I would say. I think what we're kind of experimenting with is like using like diffusion policies to like onboard new classes of ingredients, right? kind of inspired by the mobile Aloha work, and then kind of using
Like mustard's like ketchup and like barbecue sauce. They're all sort of the same
so,
class.
like the way we kind of think about it is like production data for us has been very useful to go from to kind of say, okay, we can go from like diced turkey to diced chicken. Okay, like production data is very good for that, right? Or like another trivial example might be like black beans to like brown bean or like white beans, right? Like
Pinto beans, yeah.
Yeah, exactly. So real world data is very good for that. But what if you want to go to a completely new task set? Like you want to like pick like long green beans or like sheets of lasagna. So it's a completely new class of material. I think we're experimenting with that. It's a new kind of endeavor. And then that kind of the diffusion policy idea gets you like a starting policy, right, on how to manipulate this new class with like whatever X demonstrations, and then RL can allow you to make that a lot more robust and actually get better over time and be a little bit more robust in the real world. So, but again, it's very early right now, I would say, and we use like something like Isaac Sim to like do that work.
Yeah, on my end, two different areas. One is I've seen a lot of work done on visual data, like image data and that kind of stuff. But again, like the physics side of things is sorta. And so I'd love to see more development there. Maybe I'm just not up to date. But the other area we've been pretty successful, at least getting started in early days, is using reinforcement learning and regs to generate new abstraction layers for new vehicles. So today the pipeline is new vehicle comes to us, it has some weirdo industry-specific interface. We have to code that weirdo industry-specific interface to make it abstract so that the rest of our stack doesn't care. Instead of doing that by hand, we're trying to pull in the documents and auto-generate that as much as possible through kind of LLMs and our own internal reg of here's how we build stuff and this is what it should look like. And the simulation pipeline there that we want to build is basically once we have designed that and we can't live test this thing that an auto system spat out onto a giant vehicle, we want to try to live test it against a target. And I think that's where we want to close the loop.
So we're not doing a ton of reinforcement learning today, but from past experience, I think kind of the biggest pain points I've seen of using simulation for reinforcement learning were specifically like how fast it could actually run, and then also how much compute it requires to be able to run successfully, especially like the more advanced physics models or things that like actually represent real world. And so I think that like having developments there, I think would be a really like big lift for like making this even more possible for robotics.
Yeah, plus one. I started out my career doing reinforcement learning in sim for like in traffic sims, and I've since moved over to doing mainly testing. And there is these differences in requirements. So with testing, you can parallelize basically infinitely, which means you don't really care very much if the sim is slow. But in reinforcement learning, you're trying to do gradient descent, so you want to like take the outputs of tests and feed them into new tests, and so you start to worry more. Oh, I'm so sorry. Someone's calling me. you worry more about...
It's your simulation vendor.
Yeah, right. The Matrix is... So you want to... speed is important. And that means, things that are hard to simulate or require a lot of physics to simulate get harder. So I was actually really pleased this morning to see people showing examples of dexterous manipulation of soft things, because that's historically been, and I just don't even want to think about your problem at Chef. I know, dexterous manipulation of a t-shirt is hard enough, let alone rice and whatever else. And so I think clearly it depends upon the quality of the simulation, what's the reality gap, and how fast can it run as to whether you can actually really take advantage of it in an RL context.
Yeah, plus one. So I've done manipulation in the past. I think that's the hardest thing to simulate. Like getting the physics right, is very difficult. So you're either spending a lot of time actually trying to get the physics right, and then the simulation takes a really long time to run. Or you're just kind of like approximating it, and then like you have like the gap between sim to real is just like very, very large. I think one of the advantages of being in like either self-driving or autonomous tractors is that like you don't actually really want to like touch things in the environment so much. Like you kind of have done something wrong if you're colliding with things in your environment. And so, like for that application, the ability to like do things like reinforcement learning and use simulation is actually like much more palatable. And so there you're looking for things like Simon was saying, like how quickly can you parallelize this? How many can you run? How much variations can you run against so that you can really train models against like the edges of the use cases there? So yeah, I think that's where I was like, if you don't have to contact things in the world, sim today is pretty good. I know that they're working on getting better physics sim. I worked a little bit with Drake, which is supposed to be a very high quality physics simulator, but it just takes a while to sim it, and then it kind of makes it impractical.
So when we drill down a little bit on the physics side of things, so like working in Gazebo, we've spent tons of time improving things for like maritime robotics, we want to do instead of a car, we want to do a boat. Well, there's a bunch of physics concerns there. So if we in most of the simulators do like FM equals MA. We don't do like fancy weird sand physics, right? But if we could, if you could sponsor like a student at SIGGRAPH to go and spend 10 years building a very high fidelity simulator for a particular physics aspect, what are we lacking? What do we need to build here to get things further along as you see it in your field? Allison's like, please don't call me.
My field doesn't interact with stuff, so I actually think the sim is like good enough. And I think we just need to take more advantage of it and do things like log-based simulation so that you can use like real-world data over and over again. But I don't know that we're not lacking any physics capabilities because we don't actually want to touch things. I think this is probably more of a question for the folks on that end.
I'd agree. I think to reframe the problem a little bit, I'd recommend we split our efforts into a non-physics accurate simulation for pathing and perception and that kind of stuff that a lot of us spend a lot of our time on anyway, and then a separate interaction-based physics simulator, right, which runs a lot slower and is a lot more precise, and I think that's probably a better bet.
Yeah, I think that's right. The cop-out simple answer is like, make really good food and deformable material simulators, but that's obvious, right? Mm-hmm. And one thought that was coming to my mind is like, so for the chef problem, we're placing on these like conveyor belts, right? These are like industrial kitchens that have conveyor belts. One thing that was kind of, and in my head, it was like, seems like a very straightforward problem. Like most of our team is from autonomous vehicles, and that's a much harder problem. You have to detect and track and do all these things in the real world. So it felt like relatively tractable to be like, okay, you have to track containers or sandwiches or burritos moving down the line, right? That felt doable. But then what we found is that even that environment's extremely highly dimensional, a lot more than we suspected. And there's just so many edge cases. So like some examples is like you would expect the conveyor velocity to be kind of monotonic, but it's very spiky. The acceleration's all over the place. The conveyor is like shaking, so sometimes it gets skewed. They're like different like slopes because these food factories are sloped. There's humans before and after, and they're like taking bowls out, putting bowls in, skewing the bowls, putting them different distances. So I guess all that to say, like, that seems like a relatively tractable problem to do in simulation. But even then, it feels like you're like, most of the learnings we had were actually like going to the field and being like, our thing doesn't work because it's failing in all these weird edge cases that are mostly driven by the humans, not driven by like in a vacuum what the system might look like, right? And it's again, nothing new. That's what you see in most robotics, right? But even that straightforward example doesn't really work so super well.
Could I jump in with one war story?
Yeah, go nuts.
All right. Who here has worked with mecanum wheels? Like, the omnidirectional wheels, you turn them in both directions, yeah. Who here has tried to simulate them? All right, I feel bad for you, man. So to put you on the spot a little bit, when I was at ClearPath way back when, we released this product called Ridgeback, which had mecanum wheels that could go omnidirectionally. And I think we fought with Gazebo simulation of mecanum wheels for like a month. And eventually, I think still to this day, if you check the GitHub code, there's just this hand of God force that moves the vehicle around when you tell it to go in a direction. So like...
Fake it till you make it.
Yeah, good enough. But to your question, if there's a student out there who wants to accurately model mecanum wheels, even slightly more accurately than hand of God force in Gazebo, please, that would be awesome.
All right, we got like 1 or 2 minutes here. I have one lightning round kind of question, but I've always said the killer app with ROS would be, I have RViz, I record a bunch of 3D image data, and bang, it instantly appears in Gazebo for simulation. Which comes to mind like, how are we getting assets in there? Is there anything you'd like to see in the asset community? here? Is there anything lacking? You guys got opinions real quick? Like, can you summarize them in like one sentence?
Asset creation is a nightmare and takes a long time. And, if you do in the old ways with polygons and trying to, build out scenes with the right levels of detail, and that I think you can spend a lot of time and it can be very, very manual. We are seeing really cool stuff with world models and the ability to sort of generate assets. And the quality, there's a different set of problems with those assets, but I think this is a really exciting time where, it's unclear how much the future is going to be based on sort of polygons or Gaussian splats. So we'll see.
I think for me, just attaining more photorealistic assets are things where when you simulate an RGB image capture, you get an image that actually represents what the world looks like and isn't detectable with kind of seams or weird pixel anomalies. And so that would be kind of my desire of the best asset to have.
Yeah, I think on my end, there's a lot of focus on the visual aspect, which totally makes sense. But we operate a lot in LiDAR, and a lot of simulators don't model reflectance, transmissivity, all of those parameters. And I haven't seen a good format to define a shape and then normal map not only reflectance and transmissivity, but all the different characteristics, surface roughness. And once you get to tools that can do that, you're deep in the land of professional animation tools, which take 3 weeks to render a frame and just not feasible. So that's another gap I see is we have basic visualization, but none of the, again, physics kind of details.
The split between sort of the gaming world and the simulation world
Exactly.
and the actual professional filmmaking world.
Yeah. Unreal Engine, you look at it and you're like, oh, I wish I had that sim. But then you look at the data and you're like, oh, it's not actually modeling the thing. It's a bunch of tricks.
I would say the same thing as Ilia. Nothing really major to add.
Yeah, just LiDAR. We just need better LiDAR sim as well. It was all cameras, but LiDAR. Any other sensors? Just anyone got any other weird sensors? I love weird sensors.
Ground penetrating radar would be a good one for localization.
I have not seen that one. That's great. So we got to wrap up here. We got to get our next guest on. Can you guys all give our panel a round of applause?